Okay, so let's start with the second talk. Yeah, let me remind you that please ask questions whenever you want. Make it like just unmute yourselves whenever you want. Ask a question. In the case there's if we get to the point where there is too many questions, I will stop you. But so anyway, let's start with Marcus' talk. So we have Marcus Tornsö from. I can see your affiliation here. You are in where? Marcus.
Yeah, Chalmers Göteborg.
Chalmers, sorry, yeah. Who will tell us about collective modes in holographic plasmas with momentum dissipation. So please go ahead.
Yeah, hi. Thanks for the introduction. And I would like to start to thank the organizer for letting me have this talk. Yeah, I will be sharing some of our latest regarding collective modes in holographic plasmas with momentum dissipation. This talk will be based primarily on work I've done together with my supervisor Ulf Gran and the collaborators Matteo Baggioli, Tobias Zink, and Amadeo Jimenez Alp. So it's primarily these two papers, but seeing as these two papers are really the latest in a series of papers towards collective modes, it will include some previous work as well. And I guess it doesn't hurt my chances of getting to talk at HoloTube Jr when I basing my talk on two papers with one of the organizers. Yeah. So this will be my outline for this talk. So I will start off by talking a bit about plasmas and collective modes, because plasmas are, in my opinion, the most important collective modes we find in our systems. And then how we take this to a holographic setting, how this primarily affects our boundary conditions, and what we have found in our studies. So first, I'd like to start off by talking a bit about what plasmas are, because maybe not everyone is familiar with that. So they are collective excitations of a charge density. And the dynamical polarization of the media is behind the restoring force. So if you just take the simple setting of an ordinary metal, and then you shift the electron density slightly, then you will shift the centroid of negative charge relative to that of positive charge. And you will have a restorative force proportional to the displacement here. So it will naturally be some harmonic solution. So that's where you find the plasma frequency. And then add a wave vector to this, and you get what is called Langmuir waves, but we will simply call them plasmas. Plasmas are these whole excitations, and specifically you sometimes refer to the quanta of them, but seeing as we're in a holographic setting, we won't have any quasi-particles in our system, so we refer to the whole excitations as plasmas. And before things get confusing, if you heard plasmas before, there are many different types of plasmas, and it can be somewhat confusing. So typically we separate longitudinal and transverse plasmas. That is, if the electric field is in the same direction as the wave or perpendicular to the wave. And then we typically separate them depending on their dimensionality. So bulk plasmas are what was the example in the previous slide, where the electric, well, it's the most natural system where the charges and the electric field live in the same number of dimensions. Codimension 1 plasmas, on the other hand, would be what you find in, say, graphene, where the charges are confined to a plane, but the electric field is, of course, free to live outside this plane. Lastly, there is this surface plasmas, which are an intermediate step between these two. So they live in the interface between two different medium. So if you, for instance, have light falling onto a metallic surface, you will typically excite a plasmon on the surface of this metallic surface. And they behave slightly different to these two, but they are they share some similarities with each of them. So why do we care about plasmons? So plasmons are very common. So they appear in all metals, and they have been used historically a lot for very simple reason that they look nice. So Romans used them early when it came to coloring glass. So embedding small metal beads in glass. When light shines on these small metal beads, they will excite a plasmon that travels along the bead and then re-emits the light in some different direction, resulting in, since different wavelengths are absorbed differently well, nice coloring effects, and also with coloring effects depending on what your angle is in regard to the light source. And I also love adding this picture of the rose window of Notre Dame. It survived the fire, and it also uses this coloring method. But today, plasmons are used for a lot. Plasmonics in its own right, scientific field, and it can be used for a lot, like nanosensing, rapid sensing, miniaturization of circuits, etc. And for the context of this talk, we need to ask ourselves about plasmons in strange metals. So this is nothing you haven't seen before, but typically when we consider the strange metal phase above high TC superconductors, then we would have something that would be an ideal candidate to study bulk plasmons or surface plasmons. Whereas the Dirac fluid phase of graphene, since it is a codimension 1 material, is a good candidate for codimension 1 plasmons. And these are, due to the wave localization, quite difficult to measure, or at least measure directly. This wave localization is part of why they are so interesting, but it also makes experiments relatively few. But there has been some progress recently, and I could probably improve this list a bit more now.
Sorry, can you explain what is this? What is wave localization? What's the problem?
So basically, wave localization is that the wave vector mismatches between what it was in the outside medium, so it comes from air, in regards to what it is inside the metal. So you can basically get an order 100 difference between here. So you need to have, to get a proper experiment, you would need to have potentially specific gratings to excite exactly the K you want. And you would need to change your grading for each wave vector you're interested in looking at. So it's basically just a mismatch between since the mismatch between the wave vector in the air and in the metal is so big, you need specific gratings to excite them.
Okay, thanks.
Yeah, and it's been a lot of experimental developments in the last few years, which is very interesting for us. So how do we study plasmons? The Romans did not know about Maxwell's equations. They just thought they were neat, but with Maxwell's equations, we know that plasmons are, well, basically solutions to Maxwell's equation without an external driving force behind them. So in Maxwell's equations, for these solutions, the dielectric function has a key role. And the standard longitudinal plasmons, I should say, this condition is very simple. It's just that the dielectric function should vanish. And from a condensed matter perspective, it's synonymous to saying that the density response to an external field should have a pole. And then, of course, there may be a lot of different solutions to Maxwell's equations that satisfy this. And typically, only the first one is called the plasma, and then higher order solutions is what we put together in what we mean with collective excitation. So we really, by trying to find the plasma, we find all the other collective excitations in this regard as well. So in quantum field theory systems, you resort to some approximations to describe them. For instance, random phase approximation. But these are not necessarily applicable for strongly coupled systems. So this is our segue to consider these systems with holography. Yeah, I don't need to say anything about this, but the point is we have some field in the bulk, and we can read off some quantity in the boundary theory. The specific field for us here that we're interested in is the gauge field in the bulk and in the boundary. So we typically use them to compute conductivities. So near the boundary, you can expand our field in orders of r, and this exponent clearly varies depending on which holographic model you use. This is from an ADS4 computation, and then you simply have this linear in r behavior. And then a short computation gives you the conductivity like this. And then for what we want to do, we would formally go like this way, and we would read off things with the holographic dictionary. We would identify things so we can formulate our Maxwell theory, and then we do the standard decomposition, and then we define our conductivity and dielectric function the usual way. But that sounds too complicated. So it's really just these 3 points that are important. From the holographic dictionary, we can read off a potential A on the boundary. We can also read off a current J on the boundary. And then we quite naturally want the boundary theory to obey Maxwell's equations, and in particular, this one. And since we read off these on the boundaries, that naturally becomes a boundary condition. So for a boundary condition, we have to choose some perturbation. So for harmonic perturbation in the x direction, and then once again, we don't add anything additional externally. This Maxwell equation just becomes this. And this can be shown to be related to one of the RP forms of the Green's function. So it actually connects back to the quantum field theory methods. And then, so this is what we have done in our research. So we have employed this boundary condition, and then what this J is depends on which holographic model you use. But I really want to stress this point that this boundary condition is very natural, but it's also non-trivial. It doesn't satisfy itself naturally. And we needed to ensure that we get this boundary theory we want. So we have mainly looked at plasmons, which means Maxwell's equations should be satisfied. And the main reason for doing this is, well, they appear everywhere in metals and only require Maxwell's equations, which we already have in the bulk. So it's very natural to enforce it also on the boundary. So as a boundary condition, it takes this form. So it's mixed, but it's also non-local. It's very difficult to say a name on this boundary condition that does not upset someone. So I will just give the form of it. And this function P here is typically very simple, but it's dependent on which holographic bulk model you use.
No, can you explain what this P is? I mean,
yeah, so when we read off our current J, it typically comes with some dependence on A prime. So this is really our current J. Right, so in this simple ADS4 here, J would just be this, right?
Okay.
But if you have some more convoluted top-down model, you can potentially have something rather complex here. But this shape clearly captures the df part of the Maxwell's equation, and then this captures most of the currents from different models. All currents we have been looking at least.
Yeah.
So
one more question: you're doing this in boundary that is 2 + 1, or it doesn't matter?
It doesn't matter, but then of course this specific expression I wrote here is only true for ADS4, right? But you can do this in 3 + 1 as well.
Okay.
So let's get into the specifics then of how we've employed this. So with this boundary condition in mind, we start off with the simplest possible model to use it. So it's just the Reisner-Nordström model, this Einstein Maxwell gravity in ADS4, and to which we add perturbations we treat in linear response. So in this simple system, this P only becomes a constant. And this constant here is just some strength of the electromagnetic interaction. I guess it would be, for some people, it would be more convenient to call it mu, because that is typically the relation you see in Maxwell's equations, but we will use mu for the chemical potential later. So we have just called it lambda here. And just with this, we get this very neat dispersion relation. So this is the real part of the mode, and the dashed line is the imaginary part of the mode with the same color. So we get one purely diffusive mode and then one gapped mode, which we would naturally identify as the plasmon. And this gap in the imaginary part we find here is actually rather non-trivial and not something the hydrodynamics of our model would give, since it does not approach 0 here. But this large damping, even at small k, is actually consistent with the experiments. So that's nice, and it's a very recent experiment as well. Yeah, and then we turned our eyes to the graphene case. So 2D plasmons or codimension 1 plasmons. So preferably you would want to have some top-down model that naturally incorporates this confining the charges to a plane in a larger space. But you can actually do it bottom up as well by simply, well, integrating out the Coulomb potential here. So integrating the Coulomb potential actually gives us this P that is now K half. And I should mention that these boundary conditions I have written out explicitly so far, they are in the longitudinal sector, but really the transverse sector works exactly the same way. And applying this boundary condition, we get this very, very famous, I would say, square root behavior, which was what would be expected from a 2D system. But also we get this linear dispersion that is in very good agreement with other computations that are valid in the hydrodynamic region. So here's hydrodynamic because everything goes to 0. Yeah. So with these very good results, we turn our eyes to better models. So one downside of the Reisner-Nordström is that it's unstable at small temperatures, so it has a mode of instability towards what we refer to as an electron cloud. So basically in our bulk model, we could support some density of charges in the bulk as well. So this we treated with a fluid Lagrangian, and it's significantly more complicated. So it has the upside that you get more parameters for your boundary theory, which is, well, a weakness of the Reisner-Nordström. There really is just one. But it's significantly more complicated, and of the results that we got out from this model, the most important one is that the results from the previous models are still there. So even at this, through this mode of instability, those results hold. And then for the focus of our most recent research is, well, how do we build better bulk models from the boundary side of things? So the most important things we are missing with just the Rice and Nordstrom is that, well, we don't have a lattice of positive ions. We just have some fluid of charges. And lattice models can be quite complicated to introduce. So we settled for a simpler one with just including momentum dissipation by introducing linear axions. And this naturally allows us to both break translational invariance explicitly and spontaneously. So to our Lagrangian, we add this term, where the index I here is both in the X and Y direction. We are still in ADS4. And this is really the same as the linear axion G thing used in their project. Right, and we have two different potentials for explicit and spontaneous symmetry breaking. So what did we find from here then? With explicit breaking, we refer to our models as a dirty plasma. And then we find this neat thing that the relaxation time we found from introducing the electromagnetic interactions and the natural relaxation time from including momentum dissipation, they add up very nicely to a total relaxation time of the system via this inverse Mathisen rule. So I would say that is the nicest result from this model. And then another interesting thing that is experimentally hard to find, to verify, is that we find this mode repulsion in the transverse sector. So turning up the chemical potential of the system at some relatively small symmetry breaking, we find that these modes start to repel each other more and more. And also at some finite chemical potential, we can shift this repulsion by tuning the electromagnetic interaction strength. Yeah, and for the spontaneous breaking, we refer to it as an elastic plasma. Due to the shape of the potential we add, we naturally get a crystal diffusion mode, which is a good sanity check of what we're doing. And then we find this very neat competition between the charged fluid regime, between a charged fluid regime and a crystal regime. So when the symmetry breaking parameter alpha is small, you typically have something that is dominated by the charged fluid. And when it's large, you get something that is dominated by this spontaneous symmetry breaking. So looking at,
you lost me there. So can you say what is the fluid and the crystal regime, and what is these lines in? Okay,
yeah. So I'm coming to that. So looking at just three different things, okay, we can see this transition quite nicely. So the dissipative fluid effects, which we can identify with like the classical viscosity, and then we can set that in contrast to the elastic effects from the shear modulus. You can see that the strengths of these cross each other at about alpha cube over mu equals 2. And then we can look at the speed of sound in the system. So with a small alpha, you have this typical conformal fluid velocity that is 1 over square root 2. So velocity squared will just be 1/2. And then you get this transition towards the maximal value, which would be sort of rigid system. And then ultimately, when looking at the plasma frequency of the system at some different interaction strengths, we see that independent of the interaction strength, this plasma frequency also breaks down at the same alpha cubed over mu. So all these three are independently indicating that there is some sort of transition between a fluid regime for small alpha and a crystal regime for large alpha. Did that answer your question?
Yeah.
Yeah, perfect. Sorry, I'm dragging on a bit too long, but we're at the conclusion at least. So what I want you to take away from this is that plasmas are interesting, and since they are ever present in all sorts of metals, I think ignoring them is optimistic at best. And that when you read about plasmas, there are many different kinds of plasmas. So you need to be careful with what you compare to. But also, I want to highlight that the current experimental results are within grasp of holography, actually. So that's very nice. And that we can potentially make predictions from holography that can be verified by experiments. So for instance, this I like this the first one here because, well, this date is before this date. So we sort of made a prediction they didn't know about. And I want to stress this mixed boundary condition really being in the center of it all. So for further things, I think the most important things is improving the models. And then there are some different plasmas we can look at and some different experimental setups that might be interesting. With magnetic fields, I think is most relevant in experiments. And I want to mention it because I was hoping we'd be done with this, so I could include it in this talk, but unfortunately not. Lastly, I want to leave with enforcing Maxwell's equations on the boundary theory is really just an example of what you can enforce. So if you have some relationship between quantities from holography, perhaps it would be good to also include that in what would be your boundary conditions. And that's it for me. Thank you.
Thanks, Marcus, for the nice talk. We have again time for questions and comments and discussions. Please go ahead. Danny, just ask. I see there's Danny.
Okay. Yeah. Hi, Marcus. So actually, this isn't the first time plasmas have come up in the holographic context. There was this work on probranes by Nico Jokela and Gilad Lifshitz.
Yeah.
And you also mentioned at the end you were looking for other possible applications with these boundary conditions. So this comes into the whole alternative quantization and anyons and things like this. I was wondering if you could comment a little bit on how your results compare to what was found in the probrane case, if you're familiar with it. Thank you.
So actually we've been working a bit with Nico as well, and Tobias was also involved in one of those anion papers. So the approach is slightly different. And I think the end results are quite different. I don't remember exactly what their results are, but if I recall correctly, they don't get this. So in their boundary conditions, they don't get this omega and k dependent boundary conditions with their anionization. And since that is central to actually getting this first term should have the shape of a df, it is quite different, I would say.
Sure, I can believe that, but one limit of the anionization is exactly just alternate quantization boundary conditions, which is fixing your A prime. But yeah, I think they don't have the omega and k exactly like you said. So
that's where we started off with this, actually.
Oh, okay. So then I wanted to ask a bit more. You talk about electromagnetism here, but really this, essentially what you're doing is alternate quantization, and this isn't electromagnetism as we understand it, right? There's no Maxwell equations.
I would say there is.
Isn't it? You're sure?
No, because the propagator is, I mean, this goes back to a paper by Whitten. So
Yeah, I was going to ask you about that. So
yeah, in the
that's one.
S duality, which is really what you're doing, what I mean, modulo this K and omega you've introduced. In S duality, the propagator in the field theory is generated by current loops. So I mean,
It's generated by
a loop involving two current operators. So you don't have any propagator to begin with, but when you integrate over the, so your current becomes a field in the problem instead. And when you integrate over it, when you integrate out the U1 current, the end result is something that looks like a propagator for the gauge field.
Mhm.
But I mean, this still isn't electromagnetism a la Maxwell. How is yours sort of?
So I think the formal answer you're looking for is that this is more related to a double trace deformation.
Mm-hmm. Yeah.
I don't know how much
Maybe
else I can say about it, but it's equivalent to a double trace deformation.
Maybe a better way to ask it is, why do you think it's Maxwell electrodynamics?
I would just say that the shape of it is the same.
Okay, but I mean, you would agree that this is not definitive at all. I mean, you could cook up some crazy thing that might do exactly the same thing that looks like Maxwell electrodynamics, but isn't Maxwell electrodynamics. I mean, in fact,
sure.
I remember.
Yes. So I had this formal slide. So we do our identifications to make sure that what we end up with have this shape of Maxwell's equation. But sure, it could formally be something different. But I think the important part is that the dynamics are the same.
I mean, Daniel, isn't this the same story as this? There's this paper from 10 years something ago where they calculated the London penetration depth of a holographic superfluid. And so the outcome, there was this discussion back then also, and the outcome was, as far as I remember, as long as you do not need propagating photons on the boundary, what people are doing here, like basically adding this coupling AJ at the boundary and seeing what the holographic fluid is doing when you perturb it by wiggling the electromagnetic field a bit is okay.
Yes, it certainly looks like electromagnetism.
Yeah, no, the point is that what you cannot capture is boundary photons.
Yes. Yeah, that was exactly my point, but it's electromagnetism on the boundary that you're trying to grasp.
Yeah, electromagnetism at the boundary, but it's all static in that sense.
Yes. Yeah, so I mean I mean that's essentially what I was getting at. We don't, it's not electromagnetism on the in the boundary theory as we understand electromagnetism. It's not Maxwell. It looks like Maxwell. That
and if you would say, if you would formulate your Maxwell's equations this way, it would fulfill the Maxwell equations.
Yes, that I agree to. But that's not enough. Having a solution that satisfies the equations is not the same as saying every situation satisfies those equations. Right?
I'm not sure, because you're really enforcing the Maxwell equation with the boundary condition. So,
are you?
Yeah, you are.
I mean, I guess what you do here is these boundary conditions effectively should induce some kind of Maxwell term on the boundary.
Yes, exactly.
It's just that you cannot take the cutoff to infinity easily then.
Okay, it depends on the dimension, right?
Can I just make a comment? I think the idea with the Whitten paper was that the way he did it was to enforce this dynamical photon on the boundary. And getting the dynamical Maxwell equations is a manifestation that we have dynamical electromagnetism.
I thought so.
I would say.
And I thought it was okay in 3+1, but you have problems with the counter terms in 4+1, right? But I really don't remember.
I think Marcus can comment on the counter terms because I think we have those under control.
Yeah, but what we showed here is just in 3+1. So here there are no problems to that needs to be addressed that way.
I may think for a second, come back with another question if other people have others. I need to think about what you've said.
Yeah, we can. Of course, you can discuss and yeah, even ask later.
Well, and I don't want to say something stupid on record.
If you want me to stop recording.
No, I should give other people a chance. So thank you.
Don't worry at all. Okay, it's more comments on this or on other things? Danny, you still have your hand raised, but I guess it's you just forgot to. Okay. More questions? No more questions? Okay, I'll stop recording.